All right, last three problems. Last three problems, and these are the last three problems from the level 3 side. So the level 3 side just consists of all work, energy problems, power problems, no momentum problems. So let's get these done. Oh, you're saying, wait a minute, there's 4 more problems. Actually, the one at the bottom we're not going to do because it relates to what I had on the board earlier, work, potential, kinetic, and then heat, but we're not going to do heat. Don't worry about it, that last problem. So not the last problem. So problems 3, 4, and 5. No. 2, 3, and 4. 2, 3, and 4. 2, 3, and 4. All right, problem 2, Cartman. Problem 2, Cartman pushes a 40-kilogram lawnmower. So let's go ahead and draw this out. You have a lawnmower. You're pushing it. So here we go, pushing the lawnmower. There's my lawnmower. So one of those ride on top of the grass lawnmowers you see once in a while. And so we have a 300 Newton force down the handle. So that's 300 newtons down this handle. Oh, yes, you know, they don't go away. And an angle. Yeah, triangle. We're going to have to make a triangle as bad, Larry, because what we want to know is how much force is making this move forward. How much force is making it move forward? Because the forward force that causes the motion in the direction that we're trying to solve the problem for. So we are going to need to know what that is. And this is 30 degrees. Now, I know what you're saying. You're saying, well, wait a minute. Don't we also have to know what this side is? Maybe I'll call this F down. Because when you're pushing down the handle, you're going to be pushing down and forward. You know, you always said figure out all sides of the triangle. Okay, we'll put it up there. You know, maybe we'll do need that. Okay, what do we need to do? We need to figure out the final velocity of the lawnmower after it moves 50 meters. So 50 meters is how far we push the lawnmower. And this is drawn to scale. Okay, that's 50 meters. Yeah, this one was 50-meter long ride on top of the grass lawnmower. You see? Oh, I see them all the time. I see a lot of things. Okay. Oh, ooh, too many markers. Ooh. Okay. So we want to figure out the velocity after pushing this with this force, and we also have, for 50 meters, a friction force, which is going to be working against me pushing. I don't need that bracket. So we're going to push, and then we're going to be slowed down by some friction. So we're pushing with this amount of force here, which is not 300, so we need to figure that out. And we're pushing with this amount of force, and it's being held back by friction, saying no with 120. So let's go ahead and tackle this problem. Now, let's figure out these two sides first, because you're going to need those two sides. Okay, this side, sine of 30, 0.5. And sine is equal to the opposite over hypotenuse. So if I multiply 0.5 times 300, I get this side equaling 150 newtons. This is the adjacent side, cosine. Cosine is adjacent over hypotenuse. Cosine of 30 is 0.866. 0.866 times 300. That's going to be about 260. Should be about 260 newtons. 260 newtons. So that is the force, at 260 newtons, is the force that's pushing the lawnmower forward, and that's the one I need. Okay, so let's take a look at this. We're trying to figure out velocity. So we're going to solve this by using energy relationships. That's what we're doing in this unit once again. Energy relationships. I use energy. Work, kinetic, potential energy. Work, energy theorem. So work, kinetic, and potential. Which ones would I use in this problem? Okay, what do we have? We have a force that we're pushing forward, and we're pushing this thing forward for a certain distance. That's a force at a distance. Yes, Michael. Very good. That is work. We're going to use force times distance. We're going to use work in this problem. What else? We want to know how fast it's going, what the velocity is. Do you have? No, you don't. No, okay. What about? Yes, we have velocity in this equation. We're going to need the kinetic energy. So our setup for this problem is work equals our kinetic energy. And that's what work does. Work gives you kinetic energy. Somebody has to push or pull something to work on something to give it motion, to give it kinetic energy. And that's how the transfer is. When something does work, it gives something else kinetic energy because you're moving it. So that is the concept that we need for this problem. Okay, do I know the force that's making it move forward? Yes, 260. Not so fast. Don't put 260 in here. 120 newtons is holding it back. So some of that 260 has to overcome that 120. Now in the last problem, we took the friction force and we added it. So that can be confusing. We added it to the other force that the engine was developing power to overcome. So that was a different problem though. We were trying to solve for the power the engine has to do, which means the engine has to do two things: accelerate the car, and that means plus, and overcome the friction. So we had to add the friction to the acceleration power to get a total power done by the engine. This time, we already know the amount of force that I can push with, and some of that has to be used to overcome this. And so you can see those two vectors, they're in opposition to each other. We have to subtract. So the work, the force times distance, is going to be the overall force. You can call it the net force. Remember that net force thing. Moving it forward, holding it back, net force. So the net force is 260 minus 120. Now we're going to be moving this for 50 meters. And 1/2 m. The mass of the lawnmower is 40 kilograms. You notice in this problem the mass doesn't cancel. It doesn't show up on both sides, so we have to have the mass in there. And the velocity is what we're trying to solve for, so that's v squared. So let's do the math. This is 140 times 50. Okay, that's 1/2 of 40 is 20. And then take the square root to get v. Okay, I'm going to do some math here to get rid of these zeros. Okay, 14 divided by 2 is 7. 14 divided by 2 is 7. 7 times 50 is 350. Take the square root of 350 and get v. Now, I don't have square roots like that memorized. I had it back in my day. Actually, I have to figure out calculate without a calculator. My first calculator had square root on it, add square root, multiply, divide, and then add square root. I thought the world was awesome because I had square root and I didn't have to figure them out anymore. I don't remember how to do that anyways. So 350, so second function, blah, blah, 350, blah, blah, 18.7 meters per second. Holy crap! So the velocity is 18.7 meters per second. No, that's, I guess, almost 40 miles an hour. That's what I'm talking about, okay? Yeah, that's what, I'm moving, okay? This lawnmower ain't for the weak, okay? Ain't for the weak, all right? That is what I'm talking about. Okay, moving it at around 40 miles an hour. Oh, you might be asking, hey, wait a minute. We never ended up using this force down into the ground. And the reason for that is because if we were to use it, it would be to find friction. This would be used to find the friction, but we don't have to because the friction was given in the problem. We were told 120 newtons of friction, so that means we didn't have to use this. If we weren't using this, then it would be a more complicated problem. We'd have to figure the friction out. We don't need to do it, so we're not going to. Okay, so we didn't use that. Okay, that's problem 3. No, lies. Problem 2, right? Problem 2. Okay, problem 3. Problem 3, Beatrice is sitting at the top of a slide. Beatrice at the top of a slide. She obtains a velocity of 80 meters per second. So here's Beatrice at the top of the slide. There she is, all ready to go. Not moving. Hint, hint. She gets to the bottom. She is zipping right along. Now she is here doing that because she's going 80 meters per second at the bottom of the slide. Whoa, now that's a slide. That's a slide. Question is, how high is the slide? So what's the height of the slide? Now there's no friction in this problem, assuming no friction. So we're going to figure out how high the slide must be, and this is all we're given. Well, we can't do this problem. We can't do this problem. You can give us enough. You can give us enough. We don't know the mass of Beatrice. We don't know anything else except just that one thing. You can't solve a problem with one thing. This is like the Grinch problem. We did the Grinch problem. And remember in the Grinch problem, at the end, I said, look, we don't really need the mass. You don't need the mass. If you want to give Beatrice a mass, give her a mass. Give her 1 billion kilograms. It won't matter. Hopefully, at this point, you know why. because the potential energy at the top becomes the kinetic energy at the bottom. And if we set those equal to each other, the potential energy, which is mgh, that's my gravitational potential energy, is equal to 1/2 mv squared. You see what happens. The mass cancels out. You don't need it. We don't need that. Well, we need more than that, though. We still can't solve it. We only have the velocity. Well, you're trying to solve for, we're trying to solve for this. We have that, and we're trying to solve for this. Well, I don't know, gee, oh, yes, I do. Yes, you do. You see, all that whining for nothing. You know enough to solve this problem. So solving for h, I am going to divide by g, and I have the velocity, and I know g is 9.8. Problem solved. Well, almost. Let's do it. All right, so h, let's put an arrow here, h equals 1/2 80 squared divided by 9.8. So the height is 6,400. 6,400 times 1/2 is 3,200. 3,200 divided by 9.8. About 10, so about 300, a little more than 300. It's going to be a little over 320 meters high is this slide. Okay, so that is 327 meters high. Now that's a slide. This slide is not for the weak. This is strong. 327, that's 1,000 feet. That's Empire State Building. That's a slide. Top of the Empire State Building to the bottom with no friction. That's how fast you would be going, Amy. That's why your hair is going crazy. That's what I'm talking about, crazy hair. All right, that is quite the slide. Okay, that one, pretty straightforward. We've done problems like this before, potential and kinetic. Now, here's the thing. We've not done a problem with friction yet. Guess what the next one's going to have? Asking us a friction in it. What would happen if I did have friction in the problem? How would I deal with that? What you do is the potential, which becomes the kinetic. If you know how much friction there is, you subtract it from the kinetic. Or because the kinetic is motion, and friction always takes away from motion. So if I knew the kinetic energy on one side, if you know the potential, is equal to kinetic. So if I know the potential and I know how much friction there is, I'll subtract it. The work done by the friction, I'll subtract it from actually either one in this case, because one becomes the other, and then you solve for V. Let's see what we do in the next problem, which does have that concept. Okay, so the next problem, we have a car sitting at the top of the hill. And the car, well, it's an inclined plane, it's a hill. So, inclined plane, triangle. So inclined plane, okay. We have a car sitting at the top. I'll draw a box. So I have a car. It's a box car. Boxcar Willie. Country music. So, sitting at the top. Now, what I don't know here is I don't know the height of the hill. I know the hill is 30-degree incline. I know the car is 2,000 kilograms. I was also told two other very important things. I know the length of the hill, and that's the incline, the length of the incline. The hill is 10 meters. And I know that as the car goes down the hill, over this 10 meters, it encounters 4,100 newtons of force, of friction force holding it back over the 10 meters. So 4,100 newtons over the 10 meters. Okay, that's what I know. Okay, well, I want to figure out how fast the car is going at the end, the bottom of the hill. So very similar to the last problem. And if it wasn't for the friction, a much easier problem where I would figure out what the potential energy is, set it equal to the kinetic energy, solve for V. We've done several of those problems. Now, I don't know what the H is, so let's go ahead and solve that now. I'm going to need how high this hill is. I have enough information to do that. You have the angle, and you have the hypotenuse of the triangle, 10 meters. So I could figure out this side. If this is in meters here, I can calculate this side and get a height in meters. All right, let's do that. So this side is going to be equal to, well, let's see, this is opposite, so sine of 30 equals This side, I'll call it h, over the hypotenuse of 10. So sine of 30 is 0.5. 0.5 times 10, height is 5 meters. So I know now that we have a 5-meter high hill. And now I'm ready to rock. At this point, I could just say, all right, potential energy, set equal to kinetic energy, solve, we're done. But we have friction that's working over 10 meters. Now this friction is doing work. When something moves along and something is trying to stop, like friction, that's a force. And that force is occurring over 10 meters. Force times distance is work. Friction is doing work. And if I multiply those together, I will get the work that friction is doing. While the car is moving down the hill for 10 meters, friction doing 4,100 newtons of force. Force times distance is work. So let's figure that out. How much work, I'll put WF, work is done by friction, is 4,100 multiplied by 10. There's my force times distance. So 4,100 times 10, well, that's going to be 4,100. 41,000 joules of work is being done by friction when this car is moving down the hill. Okay, let's go ahead and, the concept here is going to be that the potential at the top becomes the kinetic at the bottom. Nothing unusual here. Now, there is work being done by the friction, and that's going to take away from our energy that we had to give the car as it moves down the hill. So we're going to lose some of this energy over the course of moving down the hill because of this work done by friction. So let's figure out the potential energy that the car has to start with. So that's mgh. The mass of the car is 2,000. Is it 2,000 in this problem? Yeah, 2,000. G is 9.8. Height of the hill, which we just figured out, is 5. And this will give me a potential energy. It also gives me my kinetic energy. The potential becomes a kinetic if there weren't any friction. But there is friction. So all of this does not get converted into this. Some of this gets lost because work is being done by friction. So I need to get what this potential energy is and then take away, because that's what friction does, takes away this amount of energy, this amount of work, which remember work is energy, from the potential. So let's go ahead and get our potential. 2,000 times 9.8 times 5 equals 98,000. That's my potential energy. But some of that, as we go down the hill, is going to be lost due to the work that's done by the friction along that 10 meters. So this is going to be lost. So we're going to lose 4,100. So we end up with 41,000, not 4,100. 57,000 newtons of overall kinetic energy. Some of that potential got lost due to friction. That means as we travel down the hill with this much kinetic energy, that much kinetic energy at the bottom. That's the kinetic energy at the bottom. We've lost some along the way due to friction. We end up with 57,000 joules of kinetic energy at the bottom of the hill here. So at this point here, what we haven't lost of friction is now kinetic energy. And that 57,000 is now my kinetic energy. So I can set that equal to 1/2 mv squared, and now I can solve for v. So I can't just go ahead and use the potential at the top because I do lose some. So it's not going to be the same. Subtract away what friction does. All right, so this is going to be 1/2, that's 1,000. So this is 1,000. So let's get rid of 3 zeros. So v squared is equal to this, square root 57 equals v. Okay, so square root of 57, so 57 square root 7.55. The velocity will be 7.55 meters per second at the bottom of the hill after taking away the work loss done by friction. All right, that wraps up our problems for this page and this page and for the week. And so now we're just going to give you another small video after this. It'll be on power, and it's going to be your lab. You have a lab this week, and it's going to be on calculating your power. And after a quick break, we'll come back and get that power loaded in, and you'll be ready to rock on your lab for the week. See ya!